So in this lecture we want to find out when is a Galois group a subgroup of an alternating group. So in the lecture on transitivity of Galois group, we showed that Galois group is always a subgroup of a symmetric group or group of permutations Sn, and we know that this alternating group is a normal subgroup of group of permutations. So in this lecture we are trying to restrict this Galois group even further. So since we are talking about Galois group of a polynomial f, we have to have this f a separable polynomial. So say you have a polynomial f which lies over some field f, and in some splitting field you have its factorization like this: I equals to 1 to n x minus alpha I. So obviously you have these roots alpha 1, alpha 2, all the way to alpha n. So we put them in ascending order, and from this we have two important constructions. So first construction is you construct this delta f, which is you just take the difference of two roots alpha I minus alpha j, but I is less than j. And then we have d of j, which is just square of this. So you just take square right here. But again notice that I is less than j. So this is called discriminant. So this d of j is called discriminant. So again delta f is just difference of two roots, but you have to arrange them in ascending order so that this alpha I and alpha j you have the difference, but this I is less than this j. So same here, I is less than j, you're just squaring it. So now an important remark which we are going to use. So every permutation of this set, so this obviously gets permuted by Sn. So every permutation like this can be written as two cycles, which are also called inversions. And the signature of this permutation assigns -1 to odd number of two cycles and +1 to even number of two cycles. So obviously we are talking about permutation group because as we have seen before, Galois group is a subgroup of permutation group. It just permutes the roots. And here we have to talk about alternating group, and we know that alternating group is a normal subgroup of Sn, and this consists of just even number of two cycles. So let us see an example. So say you have permutation like this 1 2 3 4 5. So you can write it as two cycles. So you can write it at two cycles. So you keep 1 always in the front like this in all the permutations, and you start with the last one. 5 is here, then 4 is here, then 3, then 2. So count them 1 2 3 4. So there are 4 two cycles, and so the sign of this permutation, so sign of this permutation is just +1 because there are even number of two cycles. So if you just had 1 2 3 4, then this would become, this is standard technique, you have start with 1 4, you always keep the first element there, then 1 3, and then 1 2. So the sign of this permutation or the signature of this permutation, you have odd number of two cycles 1 4 1 3 1 2. So there are 3 of them. So signature here is -1, and that's what we are saying. It assigns -1 to odd number of two cycles and +1 to even number of two cycles. And in fact the proof of every permutation can be written in two cycles is precisely this algorithm. You have a1 a2 all the way to am. So this is some permutation, and then you write it as two cycles. So you keep a1 fixed in all of them in the front, and then you start with am, then am -1 all the way to a2. So you have been able to write any permutation as a product of two cycles, and then you count how many two cycles are there. So now let this f of x be a separable polynomial with some splitting field E. So we are obviously going to talk about its Galois group. So you have this Galois group of this polynomial, which is group of automorphisms of E which fix f. So this is our polynomial, lies over f, and this is how it splits in some splitting field. We are saying that splitting field is E of this polynomial. So now you take some sigma in our Galois group. So as we have seen in the lecture on transitivity of Galois group, that this sigma is nothing but a subgroup of the permutations. So the Galois group is a subgroup of our permutations. So this sigma is going to do nothing but permute the roots. So you apply sigma to our delta f, you apply sigma here, so that is, it's going to permute these roots, that is permute this index I and j. So, and this is nothing but, you say it is sine of sigma delta f, because it's just going to permute these two roots, and these two roots just form a 2 cycle. So you think of this as 2 cycle where I is less than j. So this sigma of some delta f will just keep delta f as such, but apply a sign of permutation to it. So just permuting the roots, everything else is remaining the same. Anyway, if it's a group of automorphisms of E which keeps f fixed, so it's going to permute the roots, and only thing is going to change is the sign. So if there are even number of factors, so say there are even number of factors, that means there are even number of 2 cycles, because any 2 roots give you a 2 cycle. So if there are even number of factors, that means you will just get plus 1. Even number of factors, you know, every factor you permute it gives you minus 1, and all minus 1 to the power of even will give you plus 1. If it is just odd numbers here, then you get a minus 1. So this is what this means, nothing much, because this is just a 2 cycle here of ij. On the other hand, if you apply this permutation to df, you just get df, because if you permute here, you will always get the sign as plus 1, because you have a square here. So once you permute, you get a negative sign, but then you have a square, so it gets plus 1. So this permutation fixes df. So again, notice that sigma lies in the Galois group, but we have shown that the Galois group is a subgroup of group of permutations. We're writing n here because we have precisely n roots for our polynomial. So this sigma does not change df. So you know, sigma lies in gf, which is group of automorphisms of E which keep f fixed. So since it fixes df, therefore df has to lie in f, because all permutations of our Galois group fix f. By definition, it has to lie in f. Now say this delta f is non-zero. So this delta f is non-zero. So this permutation sigma will fix delta f if and only if sigma lies in an. So what does this mean? So again, I'm going to copy this right here. So this fixing means that the sigma is going to fix delta f, means that sigma of delta f is equal to delta f. But we have the sign of sigma here. So that means we want sign of sigma always to be plus 1. So we want sign of sigma to be plus 1. The sign of sigma can be plus 1 only if you have even number of 2 cycles. So even number of 2 cycles. So because all these permutations are just 2 roots, you're permuting them, so you have an even number of 2 cycles. And you know, this even number of two cycles is precisely what is the definition of an. So this is the definition of alternating group. So this is the definition of it. So sigma will lie in an. So then the Galois correspondence will give us this. So gf intersection an. So if there is any element which obviously is of Galois group but also lies in an, then it will fix not only f, which is going to be fixed because it's an element of Galois group, so it is going to fix f, but since it also lies in an, it's going to fix delta f. So you have this Galois correspondence. So this is one Galois correspondence established here, and then you have your original Galois correspondence that the Galois group of the polynomial over f with fixes f. So this is from our definition right here. So yeah, so if this is equal to this, then this will be equal to this, because you have these two different Galois correspondence. So you have if and only if this holds and this holds, then if there is equality here, then there will be equality here. So this equality means what? So this equality means that your Galois group of the polynomial is a subgroup of an. And this equality means what? This equality means that this delta f is an element of our field f. So the Galois group is a subgroup of an, the alternating group, if and only if this delta f lies in f. So this delta f lies in f. So notice that this delta f is nothing but square root of our discriminant. So this is discriminant, and this delta f is a square root of this discriminant. So df is a square in our field f if and only if delta f is in f. So kind of obvious, because we are talking the same thing, it's a square. So what we are saying, say 2 lies in rationals, but 2 is not a square because square root of 2 does not lie in the rationals. So here we are saying that if this delta f lies in here, then df is a square in f, obviously, because this is a square of this and this is a square root of this. So kind of tautological. So in order to check this delta f is in f, we want to use this statement here. When is the Galois group subgroup of alternating group? So to check this, you have to check whether delta f lies in f. So rather than checking this, we in fact check whether d of f is a square. D of f is a square in f. That is easier to check. So that is what we are going to do. So hence we have to check df of f is a square, and if it is a square, it would mean that delta f is in f, which would in turn imply that the Galois group of the polynomial is a subgroup of the alternating group. So for example, say you have a degree 2 polynomial, f is ax square plus bx plus c, lies over the field f. So discriminant of f is given as b square minus 4ac over a square. So this we saw in high school. There is a description of this in Dummett and Foote also. So it is important that you can see how this is derived in Dummett and Foote. So if this number is a square in f, then the Galois group is precisely A2. So if it is a square, then that means delta f would lie in f. That means this would be a subgroup of An. So you have a degree 2 here. So the maximum possible Galois group would be S2. So again, Galois group of this polynomial g of f, this is a subgroup of S of 2, where 2 is the degree of this polynomial. But now, since it's a square, it is just alternating group of order 2, which is just identity in our case here for degree 2. And if it is not a square, then it is the entire symmetric group S2. So S2 is nothing but cyclic group of order 2. So again, we have talked about this in our lecture on transitivity of Galois group. So another example. So say you have polynomial g, which is x cubed plus bx plus c. Then this discriminant of g is given as minus 4b cubed minus 27c square. So the complete derivation of this discriminant is again carried out in Dummett and Foote. So you can see there how this discriminant is computed. So we will just give application of this. So say you're given a polynomial f1, which is x cubed minus 3x plus 1. This is over rationals, and this is an irreducible polynomial. So this you can check by using rational roots theorem. So then the discriminant of f1 is, you use this formula, you'll get 81, which is 9 square. So therefore the Galois group of this polynomial is A3. So notice that without this result, we just knew that the Galois group was a subgroup of S3, just without this result. And our possible choices was, it could be identity, it could be A3, or it could be S3. So we can already rule out identity because this polynomial is irreducible and it does not split into linear factors. So now our two choices were left were this A3 and S3. So because its discriminant is a square, this S3 is ruled out and A3 is our choice. So again, say f2 is x cubed plus 3x plus 1. Again, this is irreducible by rational roots theorem. You computed discriminant, it is minus 135. So if it is minus 135, then discriminant is no longer a square in rationals. This is a negative number. So the Galois group is now S3 instead of A3. So again, notice that if your roots are complex, then this square will give you a negative number. So complex roots means that the square would be negative. So this is a good way to determine Galois group. So you can also determine Galois group of quartics using our discriminant method, but that requires a lot more work. And again, Dummett and Foote actually contains detailed derivations of discriminants of degree 2, degree 3, and a description of what are the possible Galois groups of quartics.